All right, let's look at our equation. Pressure is directly related to the temperature. And remember, 1 is the initial, 2 is the final. So we've got P1 over T1 equals P2 over T2. So I'm going to go ahead and write everything I know about the equation. The original pressure is at 3.2 atm. The original temperature is at 22 degrees Celsius. But keep, you can't have any gas problems in Celsius. So I'm going to convert this to Kelvin. 22 plus 273 is going to give me my temperature in Kelvin, which is 295 Kelvin. The pressure is what it's asking for, but it wants it in kPa's. If the new temperature was increased to 60 degrees. Again, we must convert our temperature to Kelvin by adding 273. That will give me a Kelvin temperature of 333. Now, we need to isolate our P2. This one's an easy isolation. If I need to isolate P2, that means T2 needs to move to the other side. I just need to multiply by P2, or whatever I do to one side, I must do to another. And when I do that, that allows my T2s to cancel on the right side of the equation. So now, my new equation is P2 equals, I'm looking at this side first, doesn't matter which way if I put the P2 on the right side or the left side, equals T2 P1 over T1. Now, let's just plug it in. I've got my T2 temperature is 333 Kelvin. My initial pressure is 3.2 atm. And my initial temperature was 295 Kelvin. So I have my new temperature times my original pressure divided by my original temperature. When I do that, I end up with 3.61 atm because my kelvins canceled out. Now the question didn't ask for atm, but it asked for that pressure in kPa. So I've got one more step to go, and using dimensional analysis, I'm going to convert my atms to my kilopascals. Remember that 1 atm equals 101.325 atm. kPa. Sorry guys. APA. Okay, here we go. That allows my atms to cancel. Now it's just a matter of math. And we get 366 kilopascals is the new pressure. Last but not least, and no difficulty here at all, because what it does is it takes the Boyle's, the Charles, and the Gay-Lussac's laws and combines them into one with a constant amount. All of these 4 laws have a constant amount. A constant amount could be 1 mole, 2 mole, half a mole. It doesn't matter because we're just looking at the change in pressure, volume, or temperature. Now, I have it on the same side. Don't be worried. It's nothing scary here. Avogadro's principle. When measured at the same temperature, pressure, equal volumes of a gas contain equal numbers of moles. That's just what I said right there. It's at a constant amount. At 273 Kelvin and 1 atm, which is standard temperature and pressure, 1 mole of any gas can occupy, oh, you know that one, 22.4 liters. This is called the standard molar volume of a gas because it's at standard temperature and pressure. So 1 mole of a gas at standard temperature and pressure would have a volume, which is constant, 22.4, and that is known as standard molar volume of a gas. Okay, so I'm not going to get too worried about Avogadro's principle. You really know it. You just didn't realize what they were called. So let's do our last problem of the evening, and we're done. Now, a combined gas law example.